Good afternoon. We'll get started in one minute or so. Thanks for joining. All right, good afternoon or good morning, wherever you may be. Thanks for joining us today for this webinar, Take Back Control of Your Software Systems and Drive Results. We're very excited that you were able to join us today, and we have some great information and insights to share with all of you regarding design quality and its ability to predict and impact results. We have two very distinguished presenters today, Dan Sturdivant, CEO of SilverThread, and Alan McCormick, professor at Harvard Business School. Dan and Alan will share their story, and they'll explain to you the theory, the practice, and the results of applying design quality and a design quality-centric approach. We are going to have a few surveys along the way. We'll ask you a few questions. Hopefully you'll have the opportunity to provide some feedback. And to do that, you'll just enter your feedback, and it'll be very simple. Also, along the way, if you have any questions, you're all in listen-only mode right now, but you can leverage the GoToWebinar control to submit a question, and we'll conclude the presentation with a question and answer period. The question and answer period will last probably about 10 minutes or so, and it will take place at the end of the presentation. So without further ado, I'd like to turn things over to Dan Sturdivant. Dan, take it away.
Great, thank you. Thank you for coming to our webinar. We're here to talk about design quality and the impact that has on business outcomes. First, I'd like to start by telling you about my experience writing and maintaining code. I've been a developer for many years in many different types of organizations of different sizes and code bases that have been around for a long time, some new, some old. And sometimes when I was working as a developer in a code base, it was very clear what to do and how the system worked. I would make changes to a system. I would add a new function or some new capabilities, and it would just work. Right? I understood what I was doing, and I would add something, and within a limited period of time, I got the thing working and tested, and everything was good. But there have been other times when I would be working in a code base, and I would do something similar. I would add some functionality or fix a bug, and it would break something that I had no idea what that even was. Right? It would be something being developed clear across the organization, someone in a different building or even a different country. I had no idea that my change would impact that part of the system because I didn't even know it necessarily existed. When you're in that kind of situation, you're a lot less productive. You have a lot more quality problems, and it's much more frustrating as a developer. So part of what I'm going to present today is based on my own challenges over the course of my career as a developer and some insights I've gained about why that has happened in various places where I've worked. Some places where things go well and some places where they don't, especially problems that seem like they can't be anticipated. Now, over the course of our time here at SilverThread, we've interviewed people at probably more than 200 organizations, including these companies, to try to gain insights into this problem that I just described and other manifestations of it. So what kind of problems are people having in large code bases that might be overly complex, and how are they trying to address those challenges? And what we found over the course of that time is that there are different facets of this problem based on the role that you have. Right? So people who are trying to procure systems, they have challenges avoiding lemons. Right? So they don't want to buy systems that are likely to be unmaintainable in the future. They don't want to pay for bad code. They want to assess agility, maintainability, and cost of this asset they're purchasing moving forward, and that they're taking ownership of, so that they can know what to expect. Right? There are people who bid on systems and because they hope to maintain them on behalf of the government or someone else. right? So they want to know what they're getting themselves into on a maintenance project. Are you going into a code base where you're going to have a number of challenges that it would be better to know about up front, or even before you're bidding on that work, so that you know what should be realistic in terms of cost and schedule and risk. And also, there are challenges that maintainers face when they are speaking with people who own the systems that they're maintaining. Let's say that you've got a government contractor and a government program manager. There can at times be a trust issue. If a contractor says, we need to spend time to improve the system, we need to refactor it, we need to pay down technical debt in it so that it'll be more maintainable in the future, the government and that contractor often don't have sort of a basis to have that conversation. It's hard to objectively view the system and have the conversation about whether you should be investing in the future. And because it's difficult to measure and have some trust in that conversation, often the refactoring or the improvements never happen, which is detrimental to the overall maintainability of the system over the course of its life. And finally, there are people who design and they improve their own software that they develop over time. And those people have challenges getting to market, improving productivity, reducing risk, and understanding what's going on in their software systems that could be leading to business outcomes that they're experiencing. Common responses when companies or organizations are facing complexity at scale, right? So you've got a large system, it might have been around for a while, and you're in a very foggy situation, and you want to improve it. And often people's responses are to use project management techniques, so throw agile techniques into the mix. DevOps is another common one. Quality scorecards, right? But to do something from a process perspective or a project management perspective to try to improve outcomes. Some people introduce development tooling, so code quality tools, frameworks, testing, and other organizations, they might put some emphasis on the people, right? So how can we get people to behave better in this system? So can we use rewards or incentives or punishments for our developers to make them behave better within this code base? Or, it might come to the point where they decide that teams or people have to be replaced based on performance. And these kind of interventions have mixed results. Sometimes they're appropriate, sometimes not. But often people are not attacking the root cause of the problems that you're experiencing on these projects. And what we're going to focus on today, and one thing I've come to learn working with Alan and Carlos, is that often this is about design quality, right? So some systems have properties that help developers cope with complexity in large systems, right? So if you've got a large software system that's beyond the bounds of human understanding, meaning that there's no one who can understand the whole thing, but if you make it modular, if you worry about things like controlling commonality, layering, hierarchies, code quality, these are things that are potentially measurable in a code base, and where they are present, they help developers understand the code and keep it adaptable to future demands. And where those properties have broken down, those teams can be confused and frustrated, and the system can be inflexible and brittle. And this leads us to a term that some of you have probably heard, technical debt. Right? Technical debt is a term of art used to describe the situation when you make shortcuts in a code base to get something out the door quicker, but those shortcuts lead to future losses of productivity or increased quality problems. And so you can have a conversation across the business about when it makes sense to pay down technical debt by investing in code quality improvements to improve the situation. With that, I think we're gonna have our first survey question. Brian's gonna jump in and ask you a question. You can respond by clicking on some of the choices, and we're gonna tell you what all the results are shortly.
Sure. Thanks, Dan. So if you can all take a moment and take a look at the poll question and provide your response. We'll leave the poll open for about another 15 seconds or so. and we'll close this out to keep it going, and then we'll show everybody the results. All right, we've got about half of the attendees have voted so far, about 60%. It's about 5 more seconds and we'll close this out. All right, so let's close the poll. We'll share the results with everybody. So, Dan, it looks like speeding up release cycles is the winner on this poll. That 33% of those participating in the poll. So that's one of the critical things that they're trying to address as well. In very close proximity is reducing system maintenance costs and increasing developer productivity. So I think those things all go together, and which the good news is that's part of the value proposition that we're presenting today. So let me turn this back over to Alan. So Alan, I think you're going to pick it up from here.
Okay, thanks, Dan. Thanks, Brian. Good to be with you all today. Let me start by giving you a little bit of background into the work that I've done in the past and how the journey that has led me to focus on software design and software architecture. I've been a professor for around 20 years at Harvard Business School, also a few years at MIT, the competition just down the road. And I focused mainly on issues of managing innovation and product development in high technology environments, trying to understand how do you develop products when the ground is shifting beneath you, when you face a lot of turbulence in your industry and a lot of uncertainty over the choices of technologies and how customers will respond to those technologies. Now, in doing that, I've adopted a particular focus on the software industry because many of these challenges are endemic to software projects. And in fact, the earliest research that I conducted was in the mid to late 90s, looking at how internet software companies were coping with the turbulence during the first dot-com boom. And many of my examples from that early research were firms that we've heard of. Some have grown to be large and dominant, and some no longer exist now. And at least part of those outcomes perhaps can be traced to the types of processes that they have adopted. In fact, you may have read some of this early work. I believe we were the first group of people to coin the term developing products on internet time. We published a couple of articles in that vein, describing basically what today you would call an agile process. And we actually were one of the first people to show empirically over a large sample that frequent early releases to early customers and then responding to the feedback that they give you was associated with higher quality. So as an example on this slide here, we have Netscape's Navigator 3.0 browser, one of the most defining products of the internet age. It was a 6-month development cycle. It went through an iterative period of beta testing with external customers. Over the course of just 4 months, it released 6 different beta versions, and at the end released a product that most agreed was one of the most defining products of that age, and certainly better than the competing products at the time. Now, in doing this work, first of all, we learned a lot about agile processes, which many of you have probably adopted and have experience with. But what we found was agile processes didn't always work. Sometimes they ran into trouble. They didn't give the outcomes that were expected. And as we dug into the reasons why this was true, a very, very consistent message came back from managers. In projects where there is a bad design, agile methods were not delivering the outcomes that were expected. So we obviously did a little bit more probing. I'm not a software engineer by training. I'm an electrical engineer and a management scholar. So what does a bad design mean to these folks that are developing software? And it turned out that what they meant was we had a software architecture that was not modular and adaptable and basically facilitated these agile processes in terms of allowing us to make changes and rapidly move on within a project. So in actual fact, we have here a quote from some of that early research. This, for those of you who remember Alta Vista, this was actually a quote from a manager at Alta Vista during this work. And he was talking about how architectural design efforts are structured at that time to give priority not to performance but to independence. And the reason was optimizing a design typically makes it more complex and subsequently very difficult to change. So in all of this work, we just kept hearing the words design, architecture, and modularity. And what we were trying to come up with was, how do we actually think about measuring design and measuring architecture and measuring modularity in this particular context? So I kicked off a project to actually do this. So to actually take software systems, extract measures of the structural properties of those software systems, and then to capture in metrics whether a design is modular or not modular, and then trying to predict whether these different design structures actually led to better business outcomes. So methods that we use actually combine some pretty common software engineering techniques with tools from engineering management, and in particular network analysis tools. So I have an example up here on the page. What you see on the left is the very, very first version of Linux, which is the 0.01 version. It consists of 45 source files. And on the left, you see kind of a typical representation that a software engineer or software architect would look at, which is the directory structure of the program, of the application. Now, when we look at the left-hand side, it actually looks rather modular, right? We divided this system into 6 different directories, and within these directories, we have the components or files themselves. But it turns out diagrams like this, they just don't tell the whole story. And what they don't tell you is that actually there's many, many interdependencies between these different subsystems, between these different files that are not captured by high-level views. So in our efforts, what we did was we extracted these dependencies using existing commercial tools and then applied our own secret sauce, if you like, which is our network analysis tools, to display all of these dependencies in what we would call a network graph. So that's what you have on the right-hand side here. Every dot represents a dependency between 2 different source files. So if you look on the right, row number 1, we've got a dot in row 1 and column 3. So that means that file 1 depends upon or uses file number 3. So why do we use these methods, and what advantages do they give us? The first thing is, you can see there's actually a ton of dots that aren't inside the boxes. The boxes here are actually the directories. So what we can do is discover dependencies that you didn't know about before that run across directories. And then the second super important thing that this technique allows you to do is to understand the propagation of changes across a system through both direct and indirect dependencies. So if file number 1 uses or calls file number 3, we also see in this particular diagram that file number 3 uses or calls file number 2. So file number 1 and file number 2 are actually related, but they're not related directly, they're related indirectly. And we found that the secret to understanding good design and good architecture in software is not only understanding direct coupling in software systems, because actually there's a long history of looking at direct coupling, but it's looking at the indirect propagation of changes across the software system. You can only do this through network analysis techniques. So what we do is we use our network analysis techniques to help us understand the level of coupling for different components in a system, both direct and indirect, and that helps us understand the role that those components can play inside the system. So let me give you an example of the outputs from some of the tools that we're using in this research. So on the left, we have a pretty large system. I think this one's around 20-odd thousand source files. On the left, it's organized as the architectural or the directory view. So this is the view that the average software architect would use to look at dependencies between different parts of the design. What we do is through our network analysis tools, we actually can propagate this network, understand all of the direct and indirect dependencies, and then we can resort all of these components and give them categories based upon their role inside that software system. So on the right-hand side, you see an example of a sorted network graph, sorted according to the role that different components can play. So if I take you to the top of that network graph on the right, in the green we have shared components. These are the utilities or shared components that many parts of the system will use or call, things like print.c or panic.c. In the red, we have the heart of the system. This is the core of the system. It's the largest cyclic group of components. So all of the components in that red block are connected to each other, either directly or indirectly. If you're working in the core, you would know about it because every time you make a change, there's lots of things to check. It's actually quite hard to work in the core. It's quite hard to be productive in the core. Next down, we have the periphery. The periphery are a set of components that are only loosely coupled to the rest of the system. And then finally, we have the yellow block called control components or control files. These are the files that exercise the flow of control in the system. They call out or use a lot of other files, but in and of themselves, they are not particularly used a lot. So by using these network analysis approaches, obviously we don't have to understand the full details here, but what we can do is disentangle the different roles that components in a system play and work out where the heart of the system is, where are the toughest parts of the system in terms of working on fixing defects and being productive. And we can develop measures of these systems. So visually, this is a very good way of understanding system structure, but we can also measure attributes of these systems. For example, what is the propagation cost of a system? That means, on average, if I try and change a component, how many other components could I possibly touch or affect? So that's one measure that we've used in our work. The next measure that we've used is what is the size of the core? In all systems typically have a core. We found that 3/4 to 80% of our systems have a core periphery structure, but the size of the core can vary immensely. So let me show you, this is just a short snapshot of our analytical techniques, and I wanted to give you kind of 3 basic results that we've seen in the work that we've conducted, and we also have more work ongoing. So the first thing I want to talk to you about is we did some work to just explore descriptive differences across systems that exist out there in the software world. And what we found was pretty stunning. There are really, really dramatic differences in design, differences in architectural properties, even for systems that have the same mission. This is super important because if you have a system, you can always argue that your system is very unique because it has to fulfill the requirements it does, that it needs to be tightly coupled. It needs to have a dense core. It's not possible to do it any differently. Well, in our research, we've actually seen the opposite is true. In fact, this is an example from a study we did of paired software systems where the 2 systems performed the same function, but one of them had a very modular or loosely coupled architecture, and the other had a very, very tightly coupled architecture. And in this work, what we've actually done is trace these differences in design to the actual design of the organization itself that was developing these 2 systems. So on the left-hand side, we had a very loosely coupled organization with multiple teams operating independently. And on the right, we basically had a bunch of Uber hackers, as the chief manager called them, a co-located team that was put together under significant time and market pressure and produced a design with incredible numbers of interdependencies. Not surprisingly, the guys on the right found that ever-increasing amounts of their software development resources were consumed by maintenance effort. So every new release, up to 1/3 or more of their effort was devoted to maintenance. So that was the first result that we achieved, was there's a lot of diversity, and the diversity is not explained by the function of your software system, right? So there are other factors at play here. The second piece of work that we did was we took these different categories, these different roles for components in a system, and we broke them out and looked at the performance consequences of these different attributes. And what we found in these early studies was, first of all, the more tightly coupled core components are 20 times more likely to experience defects and 20 times more likely to have lots of defect activity within them. And we also found that developers working in the core, or the spaghetti as we fondly like to call it, are 60% less productive than developers that are working elsewhere in the architecture. The graphs that you see on this chart are actually 2 different studies. We have several ongoing ones that basically confirm these results. And a very, very important thing to realize here, some of these differences are explained by the characteristics of the files themselves. That is, that they have larger numbers of lines of code, or they have larger complexity in terms of a McCabe measure, but actually more than half of the explanatory power is associated with measures of the network, with measures of where in the network these components lie. So the second big finding for us is the role, the component coupling, and the presence of different types of components in an architecture totally predicts outcomes that we care about a lot. And we're actually expanding our database now to look at other outcomes that we care about, such as security. Now, the final thing I'd like to tell you about is, well, all of this is very well, but what if you can't do anything about it? So we really needed to look for examples where people had taken systems where they had properties that were undesirable in terms of design, and they'd made a significant impact. And one of the poster childs in our database of that is the Mozilla browser. So as you may remember, it was on my first slide. I actually looked at the development process of this Mozilla browser back in 1998. Then in 1998, they released the software for this browser onto the internet. And what we found by analyzing the first design that was released was it was very tightly coupled. It had a core that was 33%. It had a propagation cost of 18%. And so as time went on, contributions to this open source project, the Mozilla open source project, started declining, quite understandably so, because it was really hard to contribute without breaking something somewhere else in the system, just as Dan had described earlier on. So in the fall of 1998, a small group of people worked for 3 months to refactor the design with the pure objective of making the design more modular. They were not adding new features or new functionality. All they wanted to do was make sure that this design was more adaptable into the future. We can see the results. They succeeded in reducing the core by half, from 33 to 15%, and they succeeded in reducing the propagation cost of the system from around 18% to 2% afterwards. And thereafter, it was much, much easier to contribute to this project. Productivity soared for open source developers working on Mozilla, and of course, they eventually had success in the marketplace because of that. So I hope I've left you with a sense that, first of all, there's really sound analytical techniques at work here to understand good designs and good design quality. Second of all, that these factors actually predict outcomes. And third of all, there's hope. You can actually do something about this, especially if you can assess and use tools like these to understand where you're starting from. And that really was the genesis of Silver Thread as a firm. So let me hand it back to Dan and Brian now.
Okay, we're going to be doing our second poll here.
Sorry, I was on mute. Okay, let's launch the poll. So what tools and techniques are you currently using in order to solve your organization's software challenges? So if you take a moment, I'd love to get your feedback on this. We'll leave this open for about 20 more seconds. About half of you have voted so far. Up to about 60%. So we're going to close it here in about 5 seconds. Super. So 70% of the attendees have voted. Let me just share the results with you. So looks like agile is a popular solution. Project management tools, of course, and automated testing. So you know, this is some pretty typical, Dan. I'm imagining, with what you've seen in other places. But I will turn this over to you and continue on with the presentation.
Great. Thanks, Brian. Wonderful. So now we're going to talk about practice and Impact. We founded SilverThread as a firm a few years ago to offer solution services products around improving design quality and driving results, measuring business outcomes and the like. I actually, earlier I told you that I was a software developer for many years and had encountered a number of these kinds of challenges. I actually met Alan when I was in graduate school at MIT, came across his work and read it, and it seemed like it explained a lot of the challenges that I had faced as a developer. So I was very interested in working with him, and so worked with him and Carlos Baldwin over a number of years to do some studies. And we have decided since that we should create a commercial firm to provide these services to government organizations and firms who are interested in their outcomes. So here's what we're focused on, right? So there are lots of code quality tools that exist currently. Code quality tools like Sonar, like Coverity, like HP Fortify, tools that identify problems within a code base that might reside on a specific line of code that's identifiable that you can go clean. In the case of something like SonarQube, it'll say there's some bad practice or some rule that you violated, and if you go clean those issues, then your code will, according to various best practices, be in better shape. Things like Fortify will identify security or potential security vulnerabilities. Tools like Coverity might go identify, where there's a buffer overflow or a pointer that's being used after it's been freed. Alan just described one of the things that we're focused on as well, which is design quality, right? So using network analytic techniques to reason about, is your system modular? Is there hierarchy of modules? Is there good layering? Are the APIs clean? Is there good commonality? And these are all these are all things that you can reason about using network-based techniques. So combining those two together to reason about the state of your current code base is important. And then the other thing that we do that Alan showed some of his research on is combine that with information about business outcomes. So we've used many data analytic techniques to mine information out of not only code bases, but version control systems and issue tracking systems, financial databases, and other project management systems, so that we can do studies around what is the impact of code and design quality on productivity, on defects, on critical defects, on security exploits, on the probability that projects land on time, and other things of business value. And then what we've done is we've gone and we've created statistical and other models that allow us to link the design quality information with the business outcome information, so we can do modeling within a customer's code base and make projections about, if we measure your system and it looks like this, then the outcomes that you're experiencing may be that. And we can also build calibrated models to do that within an organization. Now, the key questions we want to help people answer are, is my system good? Does it have problems? Is it getting better or worse? What are the trends over time, right? That's important, both in steady state and also if you're doing an intervention like a refactoring. How does it compare? How can it be improved? And should it be refactored, scrapped, or left alone? We have a number of solutions that we've been developing and have developed. So we have a technology called Code MRI. These are a variety of reports and tools that we've developed to help people see inside their code. And this is aimed both at software architects, software engineers, so that they can understand the technical state of the system and have practical advice on how to improve design quality in a very real sense, right? And also for software managers or managers within an organization who want to better understand, how should I invest our financial resources so that we get the best long-term impact and the best long-term outcomes. We're also developing a tool called Code EKG, which basically is the real-time version of the Code MRI reports and tools that we're providing, but integrated into a continuous integration system so that people can have actionable information and they can easily manage a refactoring effort and do other types of assessments that you would want real-time information for. And finally, we offer professional services to help people understand design quality and business outcomes, to integrate tools into their environment, to develop custom tools and other things based on their particular problems or circumstances, and to help them assess the situation, develop KPIs, and do other things like that. So I'm going to go through some examples of work that we have done that's extends out from the research into more practical application. Right? So here is a code base for a very large firm with a product platform, and they were having a lot of conversations about why there were different parts of the code bases that seemed to be having different outcomes. Right? So they had a platform and they had many different teams working within it, and sometimes people had trouble shipping on time or cleaning up all the bugs, and a lot of those problems seem to be concentrated in one group or one cluster of groups. And what we found was, using this code MRI technology, essentially a tumor in the code base. Right? So we're finding one part of the system where you had 2,600 C or C++ files where indirectly or directly they were connected so tightly that changing one file meant that you had an upper bound probability of having a negative impact on up to 2,000 other files. And even if you have some small probability of having a negative impact on any one of them, if you do your modeling, it means that you're highly likely to have an impact on at least one of those 2,000, which explains why the majority of changes that were made to that part of the code base failed integration testing the first time through, and that's extremely costly. In parts of the code base where things were more complicated, you had 3 times as many bugs. You had a very large productivity loss amongst developers when they were working in that part of the code base relative to when they were working in other parts. And one of the things that was truly upsetting was that we found that people who spent the vast majority of their time working at the heart of that core were 10 times more likely to quit or be fired. Now, one of the things that this picture shows, and some of the other work that we did shows, is that it's not about the people, right? It's about, and it might not even be about the process. In this case, it was about the underlying structure of what they were working in. There were some people working in a part of the code base where you could not understand the code and the potential side effects that would happen when you changed it. After we produced this picture, it helped facilitate conversations, and then also we had some tools to help people have more design-based conversations around how do we improve that part of the code base to improve our situation going forward as a business. We've also recently been doing a lot of work for the United States Air Force. This is a dashboard where we are measuring these are some of the design quality parameters that we've measured around modularity, cyclicality, complexity. There are others, but this is just bubbling it up to the highest level. But we also produced, based on statistical models that we've created, projections about the business outcomes that people would experience when they were maintaining these code bases over time. And if you're the Air Force, you have thousands upon thousands of systems that are being developed and maintained that may be 50 years old up to stuff being developed today. And you want to know, because 90% of the labor that goes into these systems is during a maintenance phase, you want to be able to bend a cost curve. You want to be able to be in a situation where you are spending less over the course of that maintenance period that might extend for half a century in many realistic cases. So we're using statistical projections to say, if the current system has these properties from a design quality, from a code quality perspective, the maintainability we're projecting will be, for instance, one of our maintainability metrics is that for every 1,000 lines of code that are modified to implement features in this code base, in this case, we're projecting 145 lines that will have to be modified to fix bugs, either that are in the backlog or that are introduced by this change. In this system, we're projecting that it will take 20 or 21 days for the average software developer to create a new feature that has 1,000 lines of code. and also to debug it and ship it. So this is sort of a measure of velocity if you're using terms from Agile. And finally, time is money. So we've got in this tool some dials that you can turn around how much you pay people, but how much is it going to cost you to develop 1,000 lines of new code in this system based on its current state. Right? So this is all around how maintainable will my system be. Now here's some more detail for this project we did with the Air Force. Right? So we benchmarked many of the systems they provided to us against thousands of comparable systems. What you see on the x-axis here is the size of the system on a log scale, and what you see on the y-axis is one of our modularity metrics. Right? So actually this system looks pretty good relative to the cluster of peers around it on this one modularity metric. But possibly more interesting or important is on the right we have the business outcome projections. Right? So based on our assessment of design quality, we're able to project that 20 or 21 days to develop those new features amongst the sea of other systems that are comparable. And because of this, we can now see what is possible in terms of an improvement. It's one thing to have a static point. It's another to say, we have room to improve or not. Now, on the right, we have another measure, which is a measure of bug labor. Right? So we're projecting that within this system, 36% of the labor effort going into its development and maintenance will be to play defense instead of to play offense. Right? So how much money is being wasted on non-value-add activities, and do we have room to improve on that front? Right? Here's another slice of the same information. Right? This is, again, looking at one of these systems provided by the Air Force. What we're saying is that in our zoo of systems, the optimal code base would allow a developer creating a new feature within it to get that 1,000-line of code feature out in 14 days. Right? And the blue part of the bar represents the time spent developing new features or functionality, and the red part represents the time that is going to be spent debugging. Then you can see the system that we're assessing, how much loss is there relative to those optimal systems? How much room is there to improve? And we can use these kinds of metrics to help people understand, would a refactoring effort pay off? Right? How should you understand the maintainability of a system that is being provided by a vendor? Right? These are the kinds of questions that we can help them answer. Here's another project. This was actually done with Boeing. This was development of a technical debt balance sheet. So this is one of the reports that we provide as part of our Code MRI suite. And this was around, let's measure a code base and assess its design quality and other code-related properties, make projections about what that means in terms of how much money we are spending now on current development and how much of that money is wasted on lost productivity or increased effort to fix defects. Also, we can assess risks, so we can make projections about what is the probability of some rare event like a manufacturing line going down or something crashing, or obviously we don't care as much about that if you're developing a cell phone app, but we might turn those parameters very high if you're developing a nuclear plant. What is the cost of risk in this code base? And using all of that information, we can make projections about how much money would you save if the system was in a better state. Compare that against estimates of how much it would cost to do the refactoring, and using that information to make an ROI-based financial determination as to whether or not you should be willing to invest in a refactoring effort of a code base or not. Right now, the way that people make those decisions is, pretty much you lick your thumb, you stick it in the air, and you see which way the wind is blowing in many circumstances. And you don't have tools to either determine whether you should refactor, and also don't have tools to help you assess whether the refactoring is going in the right direction. In those kinds of environments, I would argue that today we have a systematic underinvestment in refactoring relative to what would be perfectly rational because of this lack of information. And so this tool and some of the others that we're developing are aimed at helping people understand the value of refactoring and to manage the process so that you can get better business results in your large, complex code bases. this is another example. This is a company that develops games, right? So Xbox, PlayStation, and the like. And now we're getting down into a more tactical discussion about how you improve a system, right? So in this system, this is a gaming company, and they have a number of third-party lives, many of them open source that they're dependent upon. But they have an engine that does things like worry about polygons and talking to PlayStations and Xboxes. And then there's game code, where they might have subsystems within those modules called things like character or weapon or vehicle, like that. And what we found when we scanned their code was that this shop might have many games, all reliant on the same engine, and this is a great driver of commonality. Unfortunately, as a shortcut, there was some useful functionality up in the game code that the engine team decided they wanted access to, and so they made the engine code depend on the game code, as well as having the link which you want, which would be having only the games depend on the engine. As a result, this led to a number of problems releasing code on time because the code was more complicated, and also it was harder to sort of disentangle. So what we were able to provide was specific information about where those problematic interconnections were, and some insights into how to resolve them. And finally, this is a final example. This is again a game company that we're looking at, and what we found is in this firm there were many modules that depended on the engine, and after they successfully completed a refactoring effort to break those links, to split them out so that all of their game development teams could depend on the engine, but the engine didn't depend on game code, it made it so that no game development team could make changes that would bring down the rest of the organization. They couldn't have an impact on the engine, and therefore they couldn't have an impact on the rest of the game teams. And as a result, what we see after that successful refactoring to improve the design quality of the system, the gray line that you see is the uptick in the production of revenue-generating games. So this organization was able to produce games at a much faster rate as a result of the improvement in design quality. So this isn't just about cost containment. It's also about the ability to generate new revenue, to be agile, to be flexible in the marketplace, and to get things out on time. So you can drive dramatic business results if you focus on design quality. So now it's time to flip over and do our survey number 3.
Thanks, Dan. So let me launch the poll here. So does your organization currently track software design quality, and how design quality drives business outcomes? So I'll leave this up for about 30 seconds or so. If you could be so kind, please cast your vote. We'd appreciate it. And while we're doing that, for those of you that may have some questions, we do have a queue of questions, but if you have any questions from any of the sections, the theory, practice, or results, please feel free to submit those, and we will get to those very shortly. So we have about 60% of our attendees have responded, and we're going to close the poll right now, and we'll share the results. All right. So, Dan, I don't know if you have anything to say.
Well, it seems like some of you are certainly doing this, and that's great. I'd love to hear about how you're doing it and how successful the efforts have been. Some looking to improve. That's great. Know and plan to do so, and it sounds like some of you are at organizations where you're currently not looking at these things, and maybe it's worth starting to think about if that could help. So with that, we'll back to the conclusion, and then open it up for questions. So yeah, what's up? And so here's the challenge. Does this sound like a software effort you've encountered? If you've been in software for any period of time, I suspect it is, right? Schedule, right? can you hit the deadline on time? Are open issues increasing instead of decreasing? Is your productivity stagnant or getting worse? You have agile in caps, but don't actually feel like you're really agile, according to the definition of the word in the dictionary. Do you have quality tools but have limited results? And I guess what we can help you with is we can help you assess maintainability, agility, cost, risk, and so on. Continuously improve productivity, quality, security, and prevent project failures. Help people build insight about their system via analytics and visualization. If you're interested, we can help you explore design quality, measure its impact in financial terms, and estimate the ROI of refactoring efforts. In one system or also across a portfolio of systems so that you can invest your resources wisely, and enable conversations across the organization. Help technologists have better conversations with business-oriented managers so that they can jointly make better decisions. So with that, I think we're just gonna kick it over to Q&A, and Brian, I think, is gonna read to us some questions that people have asked. You can type more questions into your little tool here for the webinar, and I think we'll have time to get to some, and others that we don't have time to get to, we will follow up and maybe have a conversation afterwards.
Sounds good. Thanks, Dan. So the first question we had came relatively early in the presentation. I think it was during Alan's presentation. And the question goes along the lines, while I think the hypothesis makes sense, how do you know that it's the structure of the code that leads to defects, interdependencies, versus a set of bad programmers? So Alan, I think this is probably best for you right now.
Okay, great. Bernard, thanks for the question. It's a really good one. In a lot of the research that we do, we adopt a set of controls, first of all, for other parameters that are known to influence productivity and defects besides the architectural measures. So these are well-known things like McCabe, lines of code, etc. With respect to the actual differences in skills of developers themselves, you have to rely upon a good research design to try and disentangle the effects. So in one particular study, if you remember back to the performance outcome slide I presented, where we looked at productivity and the difference in productivity, in fact, in that data set, what we had was a panel of developers who were developing, basically they were doing 6-month release cycles, but developers didn't work consistently in the same place. And so each developer in a given period might contribute more to the core or more to the periphery. So in that particular case, we were very fortunate to be able to adopt what we call a panel research design, where we control for developer skill. So we basically controlled out the mean level of productivity for a developer, which varied tremendously, as you might expect. And then we just looked at, like, given the same developer, like if we take a developer, whether they're good or bad, what is the average effect of moving them around to actually develop in different parts of the code base. So again, not surprisingly, out of that study, when you look at the coefficients on the developer, the number one recommendation is actually hire really good developers. But a close second is if you're doing all you can on the developer front, architecture makes a really strong difference. In the defect study that we had on the same page, we didn't have the ability to control for developer effects, because the developers themselves, even though we had user identifiers, the developers actually remained in the same part of the code base. And so at that point, it's very hard to attribute whether it's something to do with the developer or something to do with the part of the code base they're working in, or something to do with the interaction. So we know in some firms, people take rookie developers or take poor developers or take star developers, and they say, well, we better give them the hardest problems or the easiest problems. And so there's a disentanglement, basically, an entanglement of these choices. So I think the bottom line is it's a very, very good question. A number of these things are driven by developer differences, but in some of our research, we've managed to control these out, and there's still a very powerful architecture effect. Super. Well, we have a number of questions coming in, so let me jump to another one. We probably have time before
we run out here, or maybe one or two more. We have one that basically says, can you discuss projects that you have tracked over a significant time period? Maybe just give some sense of any sort of insights that you can get from that sort of observation.
Sure, this is Dan. There's one project I looked at over possibly both retrospectively and prospectively. So did some historical analysis and also looked at it moving forward. Looked at it over the course of a 10-year time window, and it was interesting. The tumors that we talk about. One thing that was interesting to realize was that we found some places in the code base that were overly complex, and it turned out that they had been there for a decade, right? And one of the implications is that you've got a lot of developers who might have been with the firm 2 or 3 years who are now wrestling with the issues in something where they didn't create the design problem, but they inherited it. And so it allowed us to turn the conversation from one in which developers were sort of being blamed for the problems. Their productivity was lower, their quality was worse, into one where we're thinking about buying them back massages and giving them combat pay because it's not their fault, right? So that was certainly one of the things that we learned by looking at something over a long period of time.
Just to add that from a research perspective, we published an article in 2012, where we did these comparisons of systems over time, and we actually show this was mainly for open source systems where we could access the source code. We actually saw in a number of cases, Linux included, that occasionally there were jumps in some of the metrics. And it's been interesting to try and work out when Linux, for example, had a pattern of getting an increasingly smaller core over time, and then suddenly there was a jump. And it seemed to occur around the time that IBM got heavily involved with Linux and devoted a lot of code to the Linux distribution. So I think it's, these measures actually, if there's discontinuities in these measures, they can actually help you to track down, causes for why a design has shifted over time. That actually was a 2014 paper.
Super. I think we have time perhaps for one more question. So let's see. We have one here. With the popularity of agile, I've never been able to get an answer on how agile efforts impact this type of analysis. Do you have any insights on agile and design quality?
Let me just say, from a research perspective, one of the very first insights that I had, it was a personal one, was having studied agile, studied the development processes that had led to the development of some of these products that subsequently became open source. When we went in and looked at the architecture, there was not a strong positive relationship between having an agile process and having a good architecture, a good design, or a modular architecture. So these seem to be things that you have to manage distinctly. And anecdotally, in a lot of the early work that I did, where people were getting tripped up when they were using agile was when they were trying to use agile on top of basically a spaghetti code base. And it's just not going to fix your problems for reasons that you will all know about. Unfortunately, it's just not a panacea in those cases. So interestingly enough, taking spaghetti and layering agile on top, it's not going to work. And then running a project from the start and just using agile and not worrying about architecture, that's actually not going to work either. You actually have to have efforts to manage process and also manage design.
Yeah, because having a highly modular system enables agile processes to work, right? If you're working at any kind of scale, right? So I'd say as you're growing a project and as it evolves, as it gets bigger and bigger, in some senses, you want it to go through some kind of cell division, right? right? First it's one part, then it's two parts, and then it's four parts, then it's eight parts. And if you do that, then you have a chance of being able to scale Agile. But if you don't, Agile is limited to small projects.
All right. Well, thank you, everybody, for your questions. I know we didn't get to all of them. We apologize for that, but we have reached the top of the hour. Dan or Alan, any final comments that you'd like to make?
Thank you. Please contact us if you're interested in just talking more. We'll follow up with people who are asking questions that we can't get to now, and hope to hear from you soon.
I think obviously, I think our email addresses are on the slide deck. Certainly like to hear about from you if you've had experiences with trying to measure software design quality, or experiences in terms of measuring the links between designs and outcomes. We realize that in this field there are actually a lot of approaches. This is one that has proven particularly powerful, and that's why we shared it with you today.
Well, thank you, Dan, and thank you, Alan, and thank you all for joining us. As Alan and Dan have mentioned, there will be some follow-up to this. If anybody that's interested in receiving a copy of the slides, please let us know. We also have recorded this webinar so that you would be able to look at this at a later time. We also encourage you that if there's anything here that's interesting that you think one of your colleagues should hear about, we'd love to meet them as well. So I appreciate everyone's time today. I hope you walk away with some insights into design quality and how it can impact the outcome, and that you'll be back for our next webinar, which should be in a couple of months. So thanks all, and have a great day.